I want to discuss this problem. It's easier than it looks. So let me first read it, and as I read it, I'll write down the information that we have. So it rains during the construction of a building, and water fills a recently excavated pit to a depth of 0.5. So here's the 0.5 meters. So we have here the pit. The water has filled to 0.5 meters. In order to continue construction, the water must first be pumped out of the pit. A hose with a length of 50 meters, so we have the L, so it's important that you know what are the variables used, and a diameter of 2.5 times 10 to the minus 2 meters, and a surface roughness of 5.0 times 10 to the minus 5 meters is attached to a pump. Note that the kinematic viscosity of water is 1.005 times 10 to the minus 6 square meters per second, and the density of water is 1,000 kilograms per cubic meter. If the pump is placed at the bottom of the pit as seen in the following figure, what is the maximum depth of the pit H for which water can be pumped out at a velocity? So we have here a velocity of 1 meter per second. Assume that the pump supplies a power of, so for the pump, of 200 watts. Okay, so for this problem you need to make a few assumptions, but first of all, remember the recommendation is to write your units. You can work with either in watts or the meters. Personally, I prefer to always use meters and then just memorize that one and use it and do the conversions as they are needed. And then of course we have the pump power here, the expression, and so I'll work out of this. If you want on your own practice using the joules per second, then you should get the same answer. Okay, so it's 0.5 meters, and I solved this problem in two different ways. You can say that this point here is 1. Of course, this is going to be 0.2, or go from here, or go from this here, 0.1. If you start from 0.1, the assumption is that that 0.5 meters will not have a significant gauge pressure. And if you work from this point here, then for sure it's from the surface really, then for sure is 0 gauge pressure, and then in 0.2 is also 0 gauge pressure. So let's if you work from this point, then you have to define this depth differently. If we work from 0.1, then the depth is directly h. And remember, if you want to give the whole h, you have to make sure that you incorporate that h in your expression. So let's see how we do this. So number one, we need we have here the velocity component, okay, and the velocity in 0.1 and 0.2 are going to be the same, so I'm using this point. I'm going to assume that, well, here is gauge pressure, so this is 0, and this I'm going to assume approximately 0 because it's not too deep. Then I have Z1, and this is my datum, so my Z1 is going to be 0. Of course, I have a pump. I don't have a turbine, and do have losses, and I'm going to say that it's only major. I don't have any other information available, so I assume they are 0. So whenever I then write this expression, what I have is that H for the pump is going to be equal to Z2 plus HL. Now, the head for the pump is, in this case, it's in meters, so I have to do the conversion. Remember then, using this expression is gamma HQ, and so what we have is the head for the pump, which is this, would be the watts divided by gamma Q. Now I don't have Q, but I can calculate it. So Q equals V times A. So 1 meter per second, and then the area is 2.5 times 10 to the minus 2 squared over 4. So my Q is 0.0005 meters per second. Okay, so then I'm going to have that H for the pump. It's 200 watts. 200 watts, and then I have the specific here. I have, so it's 1910 newtons meter cubed times 0.00005. Okay, I'm going to go to the next page. So my H is going to be equal to 40.77 meters. We take the three significant figures, 40.8 meters. Okay, so going back to the figure I had, to the expression, simplified expression for energy, HbAc2 plus 8L. This is 40.8 equals C2 plus HL. Now HL is still the major, so I need to calculate HL using the Darcy-Weisbach expression, and then the Moody diagram. Remember, the Moody diagram is a figure that instead of having to do the Colebrook equations, you have it in a diagram form instead of having to do iterations. So that's awesome. Okay, so let's then substitute for the values that we have, but then I need to find the friction factor, and for the friction factor I need the Reynolds number and the relative roughness. So let's calculate each one of those. So the Reynolds number is, I have it here. So I have 1 meter per second. The diameter is 0.25 meters. I divide this by the viscosity, 5 times 10 to the minus 6. So the Reynolds number is 24,875.6, and of course in the diagram you cannot see that, so it's about 25,000, and it's dimensionless. Now with that and the relative roughness, remember that the roughness was 5 times to 10 to the minus 5 meters. I divide that by the diameter, and so this is 0.002. Okay, so let me go to the next slide, and I'll try and make this as straight as I can. So what I have is, of course, the relative roughness is 0.002. So here's my relative roughness for my problem. So let me then find the Reynolds number. So remember that this gives you the number of zeros. So this here would be 2,000. Okay, this here would be 20,000, and this would be 200,000, 5 zeros. Okay, so here you have 20, 21, 22, 23. So it's about here. We said about, and then of course my relative roughness. So let me use the highlighter to make it a little better. So here I have my relative roughness that I'll use, and then here I have my Reynolds number. So and then mark this point here, which is my intersection, and let me see what color I can use. So more or less, I mean, we'll do it. So I have a number more or less here, and my estimation is that this is, hang on, 02, with a different number. Let me see. Well, I had actually done about 20,000, not, so let me just do it the way that I had it in my notes, because it's a little higher. So right here, let's do 20,000. Okay, and then so it would be somewhere here. So let's assume that, and in most cases I'll give you the friction factor, but then if I don't give you the friction factor, then I'm going to give you some flexibility to find that friction factor. Okay, so we get all, so let's assume it's 0.032. So now I have my friction factor, so I can calculate my loss. So I said it was 0.032. My L is 50. The velocity is 1, then square. The diameter 0.025. And if you have everything in the basic units, then you don't have to worry. And then this gives me 0.33 meters. Okay, so what I have is 40.8 equals C2 plus 0.33. So C2 equals 40.44. Okay, so when I go back to my image, that is the total depth. Now, that includes the 0.5 meters. Okay, while it's the maximum depth of the pit, well, that includes that 0.5. So this is my answer. Okay, so what I'm going to do is I'm going to prepare another recording with the last example.